Welcome friends. This video is about correlation and regression and how to implement them in different statistical software, especially in Microsoft Excel. So let us have a look at these and get started. So first let us go into the meaning of correlation. What does correlation mean and what is the purpose of correlation coefficient? Often when we deal with different variables, when we work with data, uh, the question often comes to my mind is that what is the relationship between these variables? Now, when we speak about relationship, basically we want to find out that whether there is an existence of any relationship or no relationship at all. The no relationship is generally termed as independence. So when we tell that two variables, say one variable is x and the other is y, is independent of each other, it means that there is no type of relationship which exists between the variables, and we are unable to understand the trend or pattern in one variable if we know the values of the other variable. That is the case of independence. But beyond independence comes relationship, and here we study in correlation the relationship between two variables, but more specifically correlation is studied through a measure called as correlation coefficient, and that correlation coefficient actually tries to study the linear relationship between two variables, say x and y, given a data set. Now, based on this relationship, we can divide the relationship into few parts. Like one, we can have a positive relationship. That means if the value of one variable increases, the value of the other variable also increases, and vice versa. And we may also have a negative relationship, that is value of one variable increases, then the value of the other variable decreases. So these are the different situations. First step to understand the relationship between two variables is definitely correlation coefficient. But what are variables? Variables are obviously those features whose value varies and does not remain fixed when it is measured across different subjects. For example, height of individuals. Height of individuals, if we measure the height of individuals, we will find that they are also different. And so the values of x is providing different values. So these are called as the values of the variables. Are the different variables that we encounter in our research is of same type? Obviously not. All the variables are not of same type, so we can classify the variable as quantitative variables and qualitative or categorical variables. In quantitative variables, we have those which are expressed in terms of quantities. They are either discrete or they are continuous. By discrete, we mean that these variables take some fixed values, like some discrete values, generally integral values like 1, 2, 3, 4, 5, 6, like this. Even 0 may be also one of the possibilities. These are called as discrete variables. When we speak about continuous variables, then we have a particular variable which can take any value within a given range. For example, if the height of people are measured in centimeters, maybe we will find that the height of the people are lying between 130 centimeters to say 200 centimeters. So this is actually, it can take any value within this range, and these such variables which can take any value within a possible range, even fractional values, these are called as the continuous variables. In the quantitative type of variables or the categorical type of variables, we have also some diversifications, like we can have a binomial variable. Binomial means bi means 2. So in a binomial variable, we have uh, say 0 and 1. So, or say not exactly 0 and 1, but we may have like result of the students of a class, like pass and fail. So we may give pass as 1 and fail as 0, and hence we may get divided it into two variables, two possibilities like pass and fail. A multinomial, when we have more than two categories, then it's a multinomial. It is also a categorical variable, but more than two categories. Like religion. Religion, we may have several religion of people in a gathering, and so we may have 4, 5, 6 different religions, but we may also code them like 1, 2, 3, 4. Like this, we can give some codes to this religion, but that is a different issue. But these are the ways in which we have different variables. Now let us look at the correlation coefficient. Correlation measures only the extent of relationship between variables. It was a British biometrician called Karl Pearson who provided the formula for correlation coefficient. And the correlation coefficient between two variables, say x and y, are denoted by either r then within bracket xy or r suffix xy. So this is the notation for correlation coefficient, which actually was used by Karl Pearson. And the formula has the following form, which is easier for computational purpose, and it is given by this formula, though there are different forms of the same formula giving the same result, but this is most popularly used for computational purpose. If we look at Excel, Microsoft Excel, where we will do the computation at a later stage, we will find that this formula is gainfully applied there. Other formula also exists, but are lesser in use for computational purpose. And here we see, if we want to study the relationship between two variables x and y and find what is the correlation between them, then this is, we have summation xy. That means we take the product of xy, take the sum. N is the number of pairs. So if we have 10 pairs, then n will be 10. X bar is the simple mean of the x values, y bar is the simple mean of y values, and this is summation x square minus n x bar square, and this is summation y square minus n y bar square. So this is rxy, and the range of the correlation coefficient is between -1 and +1. So these are the correlation coefficient between a range of the correlation coefficient. So this is -1 and +1. Now interpretation of the correlation coefficient. Interpretation of the correlation coefficient comes like this. That when we calculate the correlation coefficient, as we have already seen that the range of correlation coefficient lies between -1 and +1. So given the data set, if we have values of x and the corresponding values of y and calculate the correlation coefficient, then it lies between -1 and +1. +1 is both the variables move in the same direction in the same proportion. Both the variables move in the opposite direction and in the same proportion. Variables are uncorrelated. So zero variables are uncorrelated. Near zero from each side, that is very little correlation between the variates. Very little correlation between the variates. And near +1, the variables are highly dependent on each other. And near -1, the variables are highly dependent on each other, but if one increases, the other shall decrease and vice versa. However, if it is near 1, near +1, then the variables are highly dependent on each other. If one increases, the other shall also increase and vice versa. So that is the difference between +1 and -1, close to +1 and close to -1. Now you see in this table we have a few possible values of correlation coefficient, +1, -1 and 0. But these first three cases are quite almost very rarely happens in a data set or in a live data set. Only in case of some manipulated data, hypothetical data, we can produce correlations exactly +1, exactly -1 and 0. But when you go to in a research situation, or when you are actually collecting data from an live environment and then you calculate the correlation, then the last three cases, that is near 0 from either side, near +1 and near -1, are the possibilities. Not so much with the first three like +1, -1 and 0. We go on to the next slide, and in the next slide we have a problem at hand, and HbA1c test. This is a test which is commonly done to understand the average blood glucose level of different people in this. So HbA1c test, hemoglobin A1c test, is a laboratory test which reveals average blood glucose over a period of previous 2 to 3 months as long-term control test. It helps to understand the control status of the patient between checkups, and the test is not affected by brief or infrequent fluctuation in blood glucose. So this is a test quite common to diabetic patients. So below are given readings of HbA1c test values and the corresponding current blood sugar values of 10 patients. So 10 patients went to the laboratory, and then their measures were taken, like HbA1c test was done and the values were noted, and the current blood sugar level, random blood sugar level test was also done, and that was also done. And so we have this data set of the two patients. Now based on this data set, we need to compute the correlation coefficient, and the correlation coefficient is computed with the formula that we have seen just now. So yeah, let us go to Excel and have it like this particular formula. So as you can see, we are now in Excel sheet. So this is the data set that we have, and we want to calculate the correlation between these data sets. So quite long data set. You see, this is some other thing, I believe. Okay, see, so this is one HbA1c and blood glucose level, the data set that we have just now seen. Now what we do is that we come here and we write the formula for this. I can increase the view a little bit so that or I can increase the font size. Okay, so I also increase the font size simultaneously so that it looks bigger. So this is okay, fine. Now we have the formula is Correl, CORREL. Correl is the formula for correlation coefficient, and then we have we give bracket here. We take this, don't take the name of the variable, but the other things we take till the last value, one pair, and then we place comma, and then we click the first value of the other pair and click and drag to the last value. So once we do this, we close the bracket and we press enter and we get the calculated value of the correlation coefficient. So once we get the correlation coefficient 0.9982. So we need to interpret this as well. So let us close this window and come back to Excel. Okay. So come back to PowerPoint. The correlation coefficient is plus 0.99. Thus, there is a high positive relationship between HbA1c test values and current blood sugar glucose values. So this is the finding of the test, that there is a strong relationship, positive relationship. That means if the current blood sugar level goes high, the HbA1c values will also go high and vice versa. So we now proceed to the next slide. Now there is a test of significance of correlation coefficient. What is the test of significance of correlation coefficient? That we calculate the correlation coefficient, but whether the correlation coefficient is large, whether it is towards +1 or -1, that is not what is our concern. But our concern is whether the correlation is significant. Significant means something which has based on which you can tell that yes, x and y is related. For example, in the previous one, it was very clear that the value is upper limit is +1 of correlation coefficient, and this value was plus 0.99, so very close. So high correlation, obviously from the value itself we can tell, but sometimes we are in a doubt, like suppose we get 0.6 plus 0.6. Now whether it is a high positive correlation or it is something which is means not so important, not so significant. If it is not so significant, then we can tell that the values x and y are not related to each other. And if it is significant, then we can tell that yes, x and y are positively related. Similarly for negative values, so we have this data set that these are the height of sons in inches and their fathers. So these were the heights. So we want to find out that whether son and father's height has some relation with them or not. So in this case, when you calculate the correlation, it comes to be 0.603. Now whether this value, as I was giving an example also, that whether this value plus 0.6, whether it is significant. So for that we perform, this is the test, h naught rho equal to 0, so t equal to r, then under root 1 minus r square divided by n minus 2. So this follows t distribution with n minus 2 degrees of freedom. This follows t distribution with n minus 2 degrees of freedom. T equal to mod r divided by under root 1 minus r square divided by n minus 2. So this is the value 0.603 divided by under root 1 minus 0.603 whole square divided by 8 minus 2. All these values we put. So this value is the value of the correlation coefficient which you replace here. This is obviously square of that, and n number of pairs. So here we have 10 pairs. So 10 minus 2, that is 8. It is not 8 minus 2. It should be 1, 2, 3, 4, 5, 6, 7, 8. Okay, there are 8. 8 pairs. So it is 8 minus 2. That is 6. And so accordingly we compute and we get this value. So this is the value of the t statistic. And then we corresponding p value we compute. So p value corresponding to t.18515 is 0.1136. Now this is greater than 0.05, and so the null hypothesis is that the correlation coefficient is insignificant. So we go with this, that this correlation coefficient is insignificant. So based on this, why? Because it is more than 0.05. To be significant, the p value need to be less than 0.05. This is, you may take as a standard rule. So this p value is more than 0.05, that means null hypothesis, that is this hypothesis is accepted. What is this hypothesis? Hypothesis is that the correlation between the father and the correlation between the son is not related to each other. This is called as rho. Rho is nothing but another notation for correlation coefficient. So this is where we stand and how we conclude based on a test of significance of correlation coefficient. So we proceed further. And then we have another type of correlation, and that is called as the rank correlation coefficient. Now this correlation coefficient is used when the relationship between two variables that are to be studied are in terms of ranks or are such that they are measuring some attributes, like say beauty and honesty, and you want to find whether there is some relationship between beauty and honesty. Now beauty and honesty, actually these things, there are no universal scale for measuring beauty and honesty, but based on some judgment from some people, we may get a rank or a set of ranks for the subjects on beauty and a set of ranks for the subjects on honesty. And then we use a formula developed by Spearman, who actually came up with a formula for measuring correlation coefficient when data are ordinal in nature. That means we measure some latent characteristics or attributes. Once again, the range of this correlation coefficient developed by Karl Pearson is from -1 to +1. Whether the attributes, null hypothesis for this is that, for this correlation, is the attributes are independent of each other. So for example, here this is the formula, and notation is once again rho equal to 1 minus 6 summation di square n into n square minus 1. N, as you know, number of pairs participating. Di is the difference of ranks of each individual. They are squared up and they are summed. So let us have some data, then we'll understand the situation. Suppose these are 10 people, 1, 2, 3, 4, we have the names of these people. And these are the scores in a particular attribute X, which represents beauty, as you can see here. And score Y, which represents a score on intelligence. So this is, they are not in the same scale. You see, the X is in a 10-point scale and Y is in a 100-point scale probably. But then we can calculate the correlation. We don't need a scale change for this purpose. Now, how do we proceed is that we go on and rank them. That means the one with the maximum value is rank 1. So we do the ranking for X. So this is the X set. We do the ranking for it. We get this. And this is the Y set. We get a ranking for it. We get the rank this. So here, there are some problems here in the data set because, as you can see, 81 should be ranked 1, but it has got rank 2. 77 is rank 1. So this is an error anyway. So ignore it. So these we are ranking it in such a way that the topmost value will get rank 1, second topmost will get rank 2. Like this we go on. And then we compute the rank correlation. How? First we find the difference of ranks. So this is the difference of ranks. And then we find the square of the differences. So 1 square is 1, minus 1 square is 1. Like this we go on, last minus 2, that is squared up to 2. So we take a sum of this column 12 and then we replace here. So we get 1 minus 6 into 12 divided by 10 into 10 square minus 1. So this is the value of rho equal to 0.98. So 0.98 is the value of rho. For n equal to 10 at 5% level of significance, the critical value is 0.5515. So there is a table value from where we get the critical values. I think these are the critical values. So these at 5% level of significance we get. So n equal to 10. So here you see n equal to 10, the corresponding critical value is 0.5515. If the pair has 12, if there are 12 values, 12 pairs, then we will go with this. So this will be our critical value. So your calculation of rho, if exceeds the critical value, then that is significant. So here you see rho is 0.98, but critical value is 0.5515. The value of rho exceeds the critical value. So it is exceeds the critical value. So we reject the null hypothesis and conclude that X and Y are dependent. So there is a dependence, there is a relationship between X and Y, because the correlation that you have calculated that has exceeded the critical value. So this is how we make a conclusion on rank correlation coefficient. Biserial correlation. This correlation is used to calculate the extent of relationship between a binary variable and a continuous variable. So one variable is binary and the other variable is continuous, and we want to find out the relationship between the two. In such case, we take the help of a formula called as point biserial correlation. For an example, we can take that result of a test, that is 1 is representing pass, 0 is representing fail, and the intelligence quotient IQ of a group of students. If that is the thing, then we can take the help of this particular result, and then we have to compute it. Generally, it is denoted by R phi or RPBI, it's called as. The interpretation of the result of the correlation coefficient is as like that of the other values, other correlation coefficients that we have seen earlier. So what we do is that we go to the formula directly. So this is the situation. So data is provided below pertains to the emotional intelligence of 10 individuals and their answer to the question, do you love animals? Find if there is a relationship between the two variables. So these are some subjects. We have randomly taken 10 subjects, say, and whether they love animals, some of them do, some of them doesn't, and these are their emotional intelligence measured separately with a different instrument, psychological instrument, to measure this emotional intelligence. We have this data set. Now these are continuous values, however these are binary variables with values 0s and 1, and we want to find out that whether there exists any relationship between these 0 1s and this emotional intelligence. For doing this, we proceed in the following fashion, that we have, this is the formula that we have for the point biserial correlation coefficient. Let us look at these terms, what they mean. Let us have this MP is the mean of scores coded as 1. That means mean of 98, 95, 85, 89, 82 and 79. So mean of scores coded as 1. MQ is the mean of scores coded as 0, like 67, 77, 68, 71. Mean of scores coded as 0. And then we have ST, that is the standard deviation across all the scores. So this is the standard deviation. And then we have P is the proportion of scores coded as 1. And we have Q as the proportion of scores coded as 0. So these two things we have here in our data set, and then based on this we actually compute the values and we actually reach to the results. Now what we do, this is the standard deviation of all these scores. All these scores means these scores, not the binary numbers, but this continuous data set standard deviation. And P is the proportion of score coded as 1. So here we have proportion means out of 10 we have 6 coded as 1, so it is 6 by 10. And Q is the proportion of scores coded as 0, so that will be 4 divided by 10. So these values we compute. So this is the average of the values which are coded as 1. This gives me the value of MP, and then we have, these are the values which are the coded as 0, and this gives me average of these values, gives me MQ. And then we have this is the standard deviation of these values, and then we have this one is the values of proportion, that is P, that is 6 by 10, that is 0.6. We replace it here, and then we have these values, that is the proportion of Q values, negative values, that is 0 values, and so that is 4 by 10, that is 0.4. So all things we replace here and we get the ultimate score, that is 0.78. So this is the 0.78, which is the score of this R5, and this, there is a high correlation between emotional intelligence and positive response of the questions. Now look at the value of the correlation coefficient, you see it's very high. So since it's very high, so we have the high positive relationship between these variables are there. That means as the love of animals for animals increases, the value of the emotional intelligence also increases. So this is called as point biserial correlation coefficient. Next we go to Phi correlation coefficient. This is used when both the variables are categorical in nature, and if you want to find out the variables, both the variables are categorical and both of them are binary in nature. So in such a case, when we have two sets of binary variables and we want to find a relationship between them, then we have to rely on Phi correlation coefficient. Phi correlation coefficient has a range of -1 to +1, and it is denoted by R suffix phi. Let us have a data set like this. Health professionals suggest that visit to a particular country leads to infection to a particular type of fever. To test it, the following information are collected. So we have these people, 10 people who are actually 10 is for convenience we are taking, not that it is fixed for 10. It can be for any number of observations, but then 10 is for our convenience we are taking. So we have 10 number of people. They visited to different countries. Some of them did, some of them did not. A particular country, say in some country in Africa where there is a chance of getting yellow fever. So these are the people who had visited to that particular country, and these are the people who have not visited. Out of these people, 3 of them are detected with yellow fever, and out of the people who have not visited also, we have 2 cases of yellow fever. Now whether these country visit and affected by yellow fever is related to each other or not. Formula for that is this: first we convert this data into a tabular form. That means this is fever, we code it 1, no fever we code it 0. Visit we code it at 1 as 1, and no visit we code it as 0. These codes we have got from this place. Now this is the frequency, that number of people having fever who did not visit the country. That means these two, 1, 2, so this is here. And this number is the number of people who are affected by fever and who had visited their country. So these are the 3. So these are the, we are calculating the cell frequencies. Once we calculate the cell frequencies, we give it a name like A, B, C, D, and it should be in this order: 0, 1, here 1, 0. So this order A, B, C, D, and then we have this formula: A into D minus B into C divided by A plus B, C plus D into A plus C, B plus D. That means these are the product of row totals and column totals coming together all under a root sign. And then we have put these values, and these value you have found it negative, and it is 0.2. That means visit to the country is not affected by fever. We have negative correlation. There is a negative but low correlation between attack of fever and visit of the country. This seems to be no relationship between the two variables. That is, visit to the country is not the reason for that particular disease, because there are people who have not visited yet they have got the disease. So this is how we use the point biserial correlation and Phi correlation. Point biserial correlation, one data is binary and the other is continuous, but in case of Phi correlation, both the variables between whom correlation is calculated are. We have few words on correlation coefficient to end with. First is that correlation coefficient is a measure of the extent of relationship between two variables. So it does not measure any other type of relationship. For example, two variables may have a quadratic relation, they may have an exponential relation, but correlation will measure to what extent they are linearly related. So this is, you may tell, one limitation of correlation coefficient. The important thing about correlation coefficient is that the correlation coefficient is an unitary number. So whether the variable x or y are having the same unit or different unit, when you compute their correlation coefficient, they become completely free of unit. So correlation coefficient ultimately turns out to be a pure number lying between -1 and +1. And then correlation coefficient cannot predict the value of one variable when the other variable is known. Suppose I have an established relationship between x and y, but if you tell me the value of y, I cannot tell what will be the corresponding value of x. We can just tell about whether there is a linear relationship, or if there is a linear relationship, how strong is the linear relationship. That we can tell, that we can predict, but we cannot go beyond that. So this is one concern definitely. It cannot say anything about the cause and effect relationship. So whether there is any cause and effect, whether something is influencing the other, that we cannot tell with the help of this cause and effect relationship. So which one is the cause, which one is the effect, these things cannot be identified with the help of correlation coefficients. So in the next video we'll be looking into regression. Till this much in this video. Thanks for watching the video.